Hello and welcome to linear optimization. LP is a mathematical procedure for minimizing or maximizing a linear function of several variables subject to a finite number of linear restrictions on these variables. LP uses linear inequalities to solve decision-making problems involving maximums and minimums. LP is a class of programming problems in which the objective function and all other components are linear. By linearity, it means a mathematical expression in which the variables do not have powers. So we have objective function, decision variables, parameters, and constraints. What does the owner of a problem want to achieve? What is the goal of the decision maker? So the objective function can be maximization, maximize profits, production capacity, or any other measure of effectiveness or minimization type, e.g., minimize costs or losses, subject to a set of linear equalities and or inequalities called constraints. Then we have parameters. These are uncontrollable inputs. These are usually given the constant numerical values. Decision variables, controllable inputs. In any LPP, certain decisions need to be made. These decisions are denoted by xj in the LP model. Examples: number of units produced, number of hours used to produce a unit, number of people required to do an activity, etc. Xj should be non-negative, i.e. xj greater than or equal to 0. Constraints: difficulties or restrictions faced while trying to achieve an objective. They are minimum requirements needed to obtain an optimal solution. Constraints may be imposed by different sources such as market demand, production processes and equipment, storage capacity, raw material availability, e.g., in the attempting to maximize profits from production and sale of a group of products. Some constraints might reflect limited labor resources, limited raw materials, and limited demand of the products. Each can be represented by equations or by inequalities. For an LPP, the supply of resources must be limited. The management must therefore find the best allocation of its resources in order to maximize profits, minimize losses, or utilize production capacity to the maximum extent. There must be alternative courses of action, e.g., a given farm may want to produce 2 products and the problem will be to determine how much of each product is to be produced. Optimize. Subject to A11 x1 plus A12 x2 plus all the way to A1n xn, that is B1. In B2, we have A21 x1, A22 x2, all the way to A2n xn for B2 constraints, all the way to Bm, where x1, x2, all the way to xn are greater than or equal to 0. That's the non-negativity constraint. Xi's are the decision variables, Ci's are the contributions per unit of the decision variables, the objective value, Bj's are the available units of the limited resources, and Aij's are the per unit consumptions of the resources. So the objective function and constraints must be expressed as linear functions of the decision variable. Let's take an example to maximize z is equals to 4x1 plus 8x2 subject to the following. Example 2, minimize z is equals to fx1 plus 3x2 subject to the following. Note, the objective is to maximize or minimize z, which is stated as a linear function of the 2 decision variables x1 and x2. In choosing values for x1 and x2, however, 2 constraints must be satisfied, the 2 linear inequalities. So let's take a proper example. A manufacturing firm produces 2 products, A and B. Each of these products must be processed through 2 different machines. One machine has 24 hours of available capacity, and the second machine has 16 hours of available capacity. Each unit of product A requires 2 hours of time on both machines. Each unit of product B requires 3 hours on the first machine and 1 hour on the second machine. The incremental profit is $6 per unit of product A and $7 per unit of product B, and the firm can sell as many units of each product as it can manufacture. Determine how many units of product A and B should be produced within the limits of available machine capacities. The solution. The objective function of the firm is to maximize profits. The key decision is to determine how many units of product A and B should be produced within the limits of available machine capacities. Constraints: time, hour, available capacity. Decision variables xj's denote the number of units of product A and B to be produced. Constraint equation using decision variables 2x1 plus 3x2 is less than or equal to 24, i.e., each unit of product A uses 2 hours of machine 1 and each unit of product B uses 3 hours. The total hours must not exceed 24. Similarly, the second constraint is 2x1 plus x2 is less than or equal to 16. Non-negativity condition, x1, x2 greater than or equal to 0. This means the farm can produce 0 or positive amounts. So we have the objective function where we aim to maximize z is equals to 6x1 plus 7x2. The total profit is made up of the profit from product A and from product B. Example 2. A farm manufactures 2 products, each of which must be processed through Department X and Y. The table below summarizes labor hour requirements per unit for each product in each department. Also present are weekly labor hour capacities in each department and respective profit margins for the 2 products. The problem is to determine the number of units to produce of each product so as to maximize total contribution to fixed costs and profit. So we see the final formulation being z is equals to 5x1 plus 6x2, subject to 3x1 plus 2x2 less than or equal to 120, 4x1 plus 6x2 less than or equal to 260. So we have x1, x2 greater than or equal to 0. There are 2 methods of solving LP problems. We have the graphical method and the simplex algorithm. So in the graphical method, it's applicable if an LP model is stated in terms of 2 decision variables. Number 1, graphical solution approach. Formulate the problem as a LP model. Draw lines representing each constraint. Identify the feasible solution. So we have an example. First, draw the line of the constraint x1 plus 2x2 is less than or equal to 40. Next, draw the line for the constraint 4x1 plus 3x2 is less than or equal to 120. Then, sheet the region which satisfies the non-negativity restriction and the 2 constraints. The area is called the solution space or the feasible region. Any point in this shaded region is a feasible solution to the given problem. Below, we see that. Next up, we have obtain the graphical solution to the following LP model. So we have P equal to 6x1 plus 7x2 subject to the following. Our problem is to find the points or the point in the feasible solution which maximizes or minimizes the objective function. There are 2 approaches in finding the optimal solution graphically, corner point method and search method. For the corner point method, graphically identify the region of feasible solution. Determine the coordinates of each corner point on the region of the feasible solutions. Substitute the coordinates of the corner points into the objective function to determine the corresponding value. An optimal solution occurs in a maximization problem at the corner point, yielding the highest value in a minimization problem, the corner yielding the lowest value. Determine the optimal solution for the following LP model using corner point method. We have Z equal to $40x1 plus $50x2 subject to the following. So for the corner points, we found that x1 is equals to 0 bulls, x2 20 mugs, and Z $1,000. For B, we have x1 is equals to 24 bulls, x2 8 mugs, Z $1,360. For C, we found that x1 is equals to 30 bulls, x2 0 mugs, and Z $1,200. Suppose we are given a LPP with a feasible region R, an objective function P is equals to AX plus BY, then if R is bounded, then P has both a maximum and minimum value on R. If R is unbounded and both A and B are non-negative, then P has a minimum value on R, provided that the constraints define R include the inequalities X greater than or equal to 0 and Y greater than or equal to 0. If R is the empty set, then the LPP has no solution. That is, P has neither a maximum nor a minimum value. Constraints exist because certain limitations restrict the range of decision variables' possible values. A constraint is considered to be binding if changing it also changes the optimal solution. Binding constraint is one which passes through the optimum solution point in graphical solutions. Less severe constraints that do not affect the optimal solution are non-binding. A non-binding constraint is one which does not pass through the optimum solution point. Tightening a binding constraint can only worsen the objective function value, and loosening or relaxing a binding constraint can only improve the objective function value. As such, once optimal solution is found, managers can seek to improve the solution by finding a way to relax binding constraints. Every LP will fall into one of the following four categories. The model has an optimal solution. The model has multiple solutions. There is no optimal solution because the model is unbounded. There is no optimal solution because the model is infeasible. There might exist infinite number of solutions. These situations happen when the objective function is parallel to a constraint equation. We have a second theorem. If an LPP has a solution, then it must occur at a vertex or corner point of the feasible region R associated with the problem. Furthermore, if the objective P is optimized at two adjacent vertices of R, then it is optimized at every point on the line segment joining these two vertices, in which case there are infinitely many solutions to the problem. Example, maximize Z is equals to 40x1 plus 30x2. Subject to x1 plus 2x2 less than or equal to 40, 4x1 plus 3x2 less than or equal to 120, x1, x2 is greater than or equal to 0, where x1 is the number of bulls, x2 is the number of mugs. So here we see the solution. So an alternative optimal solution would be maximize Z is equals to 20x1 plus 15x2, subject to the following. An LP is infeasible if there is no solution to the LPP that satisfies all the constraints. Graphically, infeasibility means that a feasible region does not exist. The system of constraints in an LPP may have no points which satisfy all constraints. One constraint may be of less than or equal to type, while the other is a greater than or equal to type. In such a case, there is no common point in the solution set. Here, we can clearly see that. We have another problem. P is equals to 2x1 plus 3x2, subject to the following. An LP is an unbounded solution if the value of the solution can be made indefinitely large without violating any of the constraints. In LP models of real-life problems, unboundedness occurs only when the problem has been improperly formulated. Value of objective function increases indefinitely. We see the solution here. So we have a couple of questions. For the following LPPs, graph the region of the feasible solution if one exists and solve the corner points method. So with that, we've come to the end of our lesson. In the following class, we are going to be working out the solutions to the following questions. With that, thank you. Bye-bye.